everything, so it all includes the part that's uh, not getting friction from the sides and from the air.
Okay. So the bigger the cross section, the greater the percent of the water is not touching the sides, right?
Yeah.
You have a very thin trickle of water running down a stream. You have a very high percentage of that water is rubbing against the stream bed and therefore is being slowed down by friction. But as the water becomes deeper and deeper and deeper, more of the water is free to flow without intersecting the stream bed, and therefore it's able to flow faster. Right? Make sense? Yeah? No? Kind of? All right. Now, which of those, well, we'll come back to that a little bit later. All right, so that was the Manning equation, and it works for pipes, and it works for streams, and all kinds of stuff, right? And you can convert velocity to capital Q pretty easily. What does capital Q stand for? Hold on, I'm going to call on somebody. Annika, what does capital Q stand for in these calculations?
Capital Q stands for, hold on, I'm trying to find it in my notes. CFS, which is
What's the single word that we use that CFS describes?
yeah, I'm trying to find it in my notes, but I just
It rhymes with,
isn't it is it discharge now?
yeah, discharge, right? So capital discharge. So discharge is volumetric flow, right? It's the amount of water that flows past some point in the stream per second, like cubic feet per second. It's moving downstream. And how do you convert velocity to volumetric discharge, Tommy? Oh, is your microphone not working? It says your microphone's on, but I'm not hearing anything.
Yeah.
So how do you convert Q, excuse me, how do you convert velocity of the water to volumetric discharge Q?
By using the cross-sectional area,
Yeah, what do you do to the cross-sectional area?
you multiply it by the velocity.
Multiply by the velocity and you get the volumetric discharge. And then we can convert or interrelate the height of the water to the volumetric discharge, to Q, using a graph that we talked about in one of the lectures. Anybody remember what that's called? Kind of goes up and over like this. How do you know? It relates the height of the water, which is the stage, to the volumetric discharge Q. Anybody remember?
Is that the rating curve?
It is. It's the rating curve. So at any given point, usually by bridges or something, the shape of the stream, you know, like when you go over a bridge, a lot of time the stream is kind of cemented into place on either side because they don't want erosion undermining the bridge. So the stream has a pretty regular cross-sectional area. And so if you know that the cross-sectional area is staying constant over days and months and years and decades, then you can figure out how much water is, what the Q is, what the water is moving past that point for a given height of water, right? So as the water goes up, the Q goes up. As the stage increases, the discharge increases. And so you calculate these rating curves for distinct points along the stream. All right? So good? Yeah? Okay. All right, what else did we talk about? We talked about this dendritic drainage pattern that a lot of streams have. Remember what dendritic drainage patterns look like? Sort of, yes, no. They look kind of like, see if this works. You guys see that?
They kind of just look like stringy trees.
Yeah. So little things coming together like this that join up other little things coming together like this, right? So that's what's, can you see that? That's what streams look like from space, right? Lots of little streams joining into bigger streams, joining into bigger streams, and so forth. And why is it that so many river systems around the world look like that?
Because all of the water is trying to find the lowest point, and they just end up sort of like finding similar low points that on their way to flowing into the ocean.
Yeah, that's true. But if you imagine taking a perfectly flat, like imagine I took a hill that looked like this, right? And I just beveled it perfectly flat so that there were no pre-existing rivers, there were no pre-existing drainages or rills. It was just perfectly smooth. And you could even make it out of concrete. And I left that out, like pave over an entire field, nice smooth concrete, and leave it there for 1,000 years. When you come back, there will be stream systems in there that look like this.
Erosion?
So there aren't, it's not like they're always, the water is going that way because it happens to find the lowest spot, and the lowest spot looks like that. The streams are actually carving those stream valleys in that dendritic pattern. So why is it that the streams don't just create thousands of parallel? How come it doesn't look like this? How come it doesn't just look like this? With thousands of little streams all flowing that way.
Because the water it starts to connect together and it goes towards each other so it can go down faster.
So it doesn't, that's it, sort of. It's not that it wants to connect together. It's that randomly it often does connect together, right? So you have these two parallel little drops of water, and they're flowing across a field parallel to each other, and they're kind of bumping around little bits of rock, or they're moving around the root of some plant. And so they're not only going downhill, but they're kind of moving left and right. And what happens if those two drops of water come together? What's the consequence of two drops of water coming together?
They have a better ability to flow.
Right. In the microcosm, what just happened is you increase the hydraulic radius. You increase the cross-sectional area relative to the wetted perimeter. You remember this term that we were just talking about from the Manning equation? So imagine it's like a tiny, tiny, tiny little stream. The deeper you make the stream, the more water is able to flow without touching the sides of the stream, right? That exists all the way down to the micro level. So when two drops of water come together, now they're able to flow more easily than two distinct drops would if they were moving side by side. And so as little drops of rain are moving down the hill, they're bumping into each other. And as they bump into each other, they're happier, to use a weird way to describe it, right? They're able to flow more easily. So they're not going to want to separate again. And so you get this kind of dendritic pattern. Basically what's happening at the very top of the dendritic pattern is you have lots of just random little rivulets kind of moving their way until they find somebody else. They find another stream, and now they're happier and they can move better. And as those little rivulets find other rivulets, now they're even happier still because now they can really flow better. As a stream flows better, what is happening to its velocity? What do I mean by flowing better? Chloe, what do I mean by flowing better?
There's less friction since the hydraulic radius is increased, so now the velocity is faster.
They're moving faster, so they have more energy. So what is the consequence of having more energy on the ground that the water's flowing over? Sydney, if the water's moving faster, what is that going to do to the ground that little rivulet of water is moving over?
It'll probably erode it more or pick up more.
It's going to erode it, right? a faster moving body of water, a river of water, has more energy, so it can pick up and move along more sediment, right? Make sense? So the more these little drops of water come together, the faster they're going to go. The faster they're going to go, the more they're going to erode a channel. And the more they erode a channel, the more what?
The more the faster they erode a channel, then the friction of the channel will go down as they erode it, and it'll go even faster, and they can.
That's
And
probably.
wouldn't it create a bigger area?
Yeah, it's gonna, as it drops, as it incisors down, it's gonna be acting sort of like a funnel now. It's gonna be catching water from more places, right? So once it begins to incise down, it's gonna be sucking in or capturing the water that falls on the margins, which is gonna then add more water to the stream, which is gonna allow it to flow even faster and incise even more readily. So once, I put on the syllabus the other day, this thing that I totally forgot to have you do. And it might be kind of fun to do given that you're stuck at home with very little else to do. There's this little exercise you can do. It's called a random walk exercise. And let me show you how you do it. We do this in class, or at least sometimes we do it in class, depending on how much time we have, because it's kind of silly and fun, but it also, whatever. So you take a couple of spots, like call this A. Can you guys see this? I'm in a weird spot here. Can you guys see this thing I'm drawing? Can you see that?
Yeah.
Yeah. So you go A, B, C, D, E, and you do this on grid paper, you know, where you have, or like graph paper, where you have lots of little vertical and horizontal lines. Okay, and what you do is you just flip a coin, or you flip two coins, right? And if it's like two heads, you go to the right. If it's two tails, you go to the left. If it's a head and a tail, you go straight down. Make sense? So you're just flipping coins, and you are randomly determining the path that each one of this is supposed to be a drop of water. Each A through E is supposed to be a drop of water that hits a hill slope. And they're generally going to move in this direction down, but they're going to kind of zig and zag randomly because they hit rocks and bugs and whatever else, right? And so what you do is you just sort of play this little game by flipping coins to determine what direction each one of these goes, and you do them one at a time. So this one goes to here, 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 and this one goes to here, right? And then you go back and you do it again. This one goes here, this one goes here. Now these two, A and B, have just met up right there. And once they've met, because of the reasons we just discussed, they don't separate. So now they're going to continue to go wherever they're going to go, and this one's going to go this way or whatever. It's just determined by the flip of a coin. And now this one's met up with these two, right? And what you end up with usually is something that looks very much over time like a dendritic pattern. And it's due just to random, the two simple rules. The direction you go is determined by the coin flips, and whenever two streams meet up, they don't separate, right? And so you end up with what looks an awful lot like a dendritic pattern, driven just by those fundamental principles. I didn't have you do that. You might want to try it. It's kind of fun. It's like the world's most boring video game, but it's not a video game. It's not even a game. It's just boring. Anyway, that's the idea, okay? So dendritic pattern of these really, really common dendritic patterns of streams can be explained in part by gravity and by the Manning equation. Make sense? Kind of? The Manning equation is really important. It's just one of these fundamental equations. There are really two fundamental equations in hydrogeology. Manning is one of them, and the other is called the Darcy's law, which we'll get to in a day or two. And they describe water movement really well. All right. Any questions on that so far? You all good? All right. one other thing I wanted to talk about before we move too far past it was this flood recession stuff. Were you guys able to do that homework okay? Does it make sense what's happening? You remember the flood recession curves where you have a hydrograph, which is just tracking the amount of water in a stream, and you get a big flood, so the water goes up in the stream, and then it kind of decays exponentially like this. And we use this exponential decay equation to basically allow us to predict the rate at which the water level in the stream is going to drop. Anybody have any questions about that, or are you all good? Tiff, do you have a question? No? Okay. All right. Well, if you don't have any questions, we'll just keep moving, but I wanted to give you all a chance to chime in if you didn't understand something. Okay. Let's see. A couple of people had some questions about the reservoir elevation calculations that you did for homework for today. So you had that 690 acre reservoir, and you had river water coming in and river water going out, and you had rain falling and water evaporating, and you had to figure out how high the water level was. Did anybody have any questions about that? I posted the key just about half an hour ago or an hour ago to Moodle in Excel, so you can actually click on the box where the answers are, and it'll show you the equations that I used to do the calculations. But hopefully you get it. All good? Do you want another minute to look at the Excel sheet? Are some of you doing that? Are you ready to go? All right, well, we'll move on. One of the other things we talked about in the lectures was, by the way, before we talk about the content, how is the quality of the lecture? I mean, is it okay? I mean, are you able to see the paper, and you're able to hear me okay, and you're following along? It's not too, all right. All right, so the next thing, one of the next things we were talking about was infiltration. So the vast majority of hydrogeology involves groundwater. And the way I structure the class basically is we start a little bit with surface water, and then we move to infiltration, which is how the surface water gets underground. And then once we're underground, we basically stay underground for the rest of the class. All right, so you're just getting you're getting an introduction to flooding, you're getting an introduction to hydrographs and the Manning equation and that sort of thing. But most of the class will involve groundwater flow, which is quite different. So what are some things that determine how fast water infiltrates into the ground? Samantha, I'll start with you.
Like how porous the ground is.
What does porous mean? What does that mean?
Like like air spaces in the little air pockets in it.
Yeah, and right. So it's the little spaces between the empty spaces between the grains, and they're usually filled with air or water. Right. Those are basically your two options. What determines? So we use this term porosity to describe the percent of a rock or the percent of a soil that is made of empty space. What determines the porosity? What are some things that would determine the porosity?
How well sorted the sediment is.
How well sorted? What does it mean to be well sorted?
It's like well organized. Like you said, sand dunes, I think was the example you used, is really well organized because it's all the same or similar size grains. So then there's no smaller grains that can get in and clog the pores in the ground.
That's it, exactly. Yeah. So it's when we talk about sorting, we talk about arranging the grains according to size. That's what they're being sorted by. Color doesn't matter. Shape doesn't really matter. It's just the size. So if you have lots and lots of similarly sized grains, then for the reasons that I sort of diagrammed in my lecture, there's usually a lot of space between those grains. But and that's where the water would go, right? If you have poor sorting, then you get little grains in between the big grains, and you reduce the amount of porosity. So why does porosity impact the rate at which water can infiltrate into the soil?
Because if water is going to soak into the soil, it needs somewhere to go.
It needs
And
somewhere
it
to
can't move through solid grains.
Right. So the water is going to infiltrate from the surface into the pores in the soil, right? And so the more pores there are, the more space there is to hold the water. So it should infiltrate faster. Now, here's a trickier question. Does the size of the pores matter? Let me diagram something for you. Hold on. I got to go get a paper towel to wipe this off. I'll be back in 2 seconds. All right, back. All right. All right. So if you had two kinds of sediment, one with big grains like this, all exactly the same size, right? And then you had another sediment like this, all exactly the same size. Can you guys see those two there? This would be A and this is B, right? The difference, obviously, these are all identical in size, these are all identical in size. It turns out that the porosity in both of these is the same. The percent of void space, of empty space inside this box is the exact same percent void space as it is in this box, okay? But here's my question. So if the porosity is the same, the question is, will the water, the infiltration rate, be the same into A as it would be into B? Same or different? What do you think?
Same.
Raise your hand if you think it's the same. Raise your hand if you think it's different. It's pretty tight. Some of you voted both. Covering your bets. I like it. The answer is that the fastest would be this one by far. Why would the water soak in here faster than here if the porosity is the same? And the answer is one word, 2 syllables, begins with the letter M. What is it? What's the answer? One word, 2 syllables, begins with the letter M. Say it. Say it. Manning. It's the Manning equation again. The fact that these pores are bigger means that the hydraulic radius is higher, right? It's like water flowing through a big tube versus a small tube, or through a big river versus a tiny little stream. There's more friction. A greater percentage of the water flowing through these little pores is rubbing against the sides of the surrounding grains, and therefore it's slowed down by friction. Make sense? By the way, I forgot to record yesterday's video, I think. I also forgot to record the start of today's video, but I've been recording all this, so I'll post it. All right. Okay, makes sense? So what happens then to the rate at which water infiltrates into the ground as you put more and more and more water on a soil? What happens to the infiltration rate?
It decreases.
It decreases linearly. How does it decrease?
Exponentially.
Exponential decrease. And why, in the most fundamental sense, is the porosity, is the infiltration rate decreasing exponentially as we saturate the soil?
Because the amount of water in between particles increases.
And what does that do, Joey?
And that reduces the amount of water that can go into the soil.
Sort of. But what's the sort of physical effect that's being impacted by saturating the pores? Five syllables, begins with the letter C.
Capillary.
Capillarity, yeah, right. So remember what capillarity is? Capillarity is the sucking that occurs between open spaces like a straw and a liquid due to surface tension. So when you have a dry soil and you put water on top of it, it's sort of like having millions and millions of little tiny straws sticking up into the water, and those straws suck the water down, right? So they're actually accelerating the infiltration rate of the water faster than it would naturally just due to gravity. But as you fill all those pores with water, eventually it just reaches some sort of plateau, some sort of steady state infiltration rate. All right, so with that in mind, what I want you to do is go to Moodle. Can you guys see my screen right now? I don't think you can. Go to Moodle and under exercises, there's this thing called infiltration exercise. Everybody see that? So I'm going to break you out into rooms. We're going to try this for the first time. You guys are going to work in teams of 3 or 4 to answer these questions. I'll give you about 20 minutes, 15 or 20 minutes to do it. But the thing I want you to notice is, get this ready here. All of the questions in this little exercise are centered on this equation. I equals A plus B over I. See that? I mean, literally, can you see that? Tiff?
Yeah.
Yeah. So I is infiltration rate. So that's the rate at which the water is going to be soaking into the ground, and that's in, milliliters per second or whatever it's in. A and B are constants for a particular soil, constants. And you'll either be given those or you have to solve for them. And capital I is the cumulative infiltration. And that's in millimeters. In other words, how much water has soaked into the ground. All right, so let's just look at this for a minute. Let's make this infiltration rate, that's I, little I, versus total infiltration, big I. Can you guys see that graph there? There. Infiltration rate versus the total amount of infiltration, the rate at which water infiltrates versus the total amount of water that has infiltrated. What is this graph going to look like over time? So if this A is a constant and this B is a constant, as this number gets bigger and bigger and bigger and bigger, what is this term going to do?
Go to 0.
It's going to go to 0, right? Who cares what B is? Say it's 10. We don't know what it is. Who cares? It's 10. Let's say it's 10. 10 divided by 1 is 10. 10 divided by, if you increase I now to 2, it would be 10 divided by 2. That would be 5. Make I, big I, 10. 10 divided by 10 is 1. See how it just keeps getting smaller and smaller? It goes from 10 to 5 to 1. If this is a billion, right? What is 10 divided by a billion? It's essentially 0, right? So as the total amount of infiltration of infiltrated water increases, this term goes to 0. So what is the infiltration rate going to be after we've infiltrated lots and lots and lots of water?
A.
Going to be A. So whatever A is over here, oops, that's supposed to be a straight line. That's where the water, the infiltration rate is going to be over time. So what you get is this thing. Can you guys see that? You start out with some infiltration rate that's pretty high, and the more water that soaks into the ground, the more the infiltration rate decreases until finally it just reaches some steady state level, which is equal to A, and it just stays there forever. That's what we were talking about in that lecture that I gave you on infiltration. Okay, this is one way to, a very simple mathematical way to model that kind of behavior. Okay, all right. So you've got 3 or 4 questions in this problem set, and I'm going to break you out into groups, and we'll try it. I don't know how this works. I haven't tried it before. I may, if I can, I'm going to pop in on you now and then and check, but we'll just see what happens. So here we go. I'm going to try the breakout rooms. How many of you are there? 1, 2, 4, 7, 8, 9, 10, 12, 14, 16, 18, 20, 22, 23. So I'll make 5 groups. And I'm going to do this automatically. So you're randomly about to be assigned to a breakout room. And I'll see if I can pop in on you. If for some reason things go to hell, I will email you in a minute, like if I lose the connection or something. So just check your email if you don't hear from me in a bit. All right, here goes. Let's see what happens.
Oh, hello.
Hi, I'm just figuring this out. So I just popped in. You guys don't, just ignore me.
All right. You guys have the exercise pulled up?
Mhm.
Yeah, I just printed it. I'm gonna go grab it.
Oh, okay.
Yeah, I'm gonna get a notebook.
Yeah.
Minus 20.
We have the eye and then we have the big eye.
Hi guys, I just want you to know,
One.
but I don't want to interrupt you. I'm just experimenting with how this breakout room thing works.
Mhm.
Okay.
Can I ask you a quick question, Ron?
Yeah.
So for B, the constant, is that the porosity or?
No, it's just, well, I mean, it would be related to the porosity, but just think of it as a constant that's empirically derived, meaning it's derived from experimentation for this particular soil.
Okay.
So how do we know what that is for this, for the worksheet?
You gotta work it out, Tom.
Okay. Oh yeah, I guess we can solve for B.
Yeah.
That's easy. 1500. 1500, does that make sense?
Did you put for the big I, did you put 100?
Hi, I'm here with you. I'm just experimenting with this technology, so ignore me. Pretend I'm not even here. Crash on the floor here. I got to do something. You guys aren't saying anything. You're supposed to be working together. Lily?
So for 1 is the lowercase I supposed to be the cumulative infiltration or the infiltration?
That's capital I. Capital I is cumulative infiltration. Little I is the infiltration rate.
Okay.
Are you guys all doing this independently? Sam? Talk it out. I'll leave. So I don't want to disrupt your mojo, but talk it through if you're at all confused on what to do. All right, I'll be back. See you.